welcome back, everyone. And I have the pleasure of introducing the next two presentations, which are on the very important topic of nutrient loading. And again, introducing two experts that really need no introduction, especially here at APMS. But the first is Dr. Wes Bishop, who is an algae scientist and water quality research manager at CPRO and is the host of the wonderfully informational Algae Corner video series on all things algae. And Dr. Bishop's current focus includes inventing, developing, and implementing proactive and reactive solutions to improve water quality and control nuisance cyanobacteria. Dr. Bishop is a wealth of information, especially on cutting-edge technologies in algae management. So take it away, Wes.
All right. Can you hear me okay?
Yes, you're great, Wes. Thanks.
All right. And can you see the slides?
You're good to go.
All right. Thank goodness. All right. Well, welcome everyone, and good morning. Hope everyone's doing well out there. Just give me a second. I'm just rearranging my desktop here. Hope everyone's doing well. Happy New Year. Very excited to be here and be speaking with you today, albeit virtually. So hang with me through any technical hiccups if there are any, hopefully not. But as much as possible, I'd certainly love to keep this as discussion based and interactive. So Heather, if any questions come in the chat, feel free to jump in and ask them. Don't hesitate. So I know some of you probably have a lot going on and listening to other things, but I want to keep you engaged as much as possible, certainly in this setting. So I want to start, maybe a little unconventionally, just because we're virtual, so a little unconventionally with a quote. I'm not huge into quotes, but I thought this one was fitting. Just tell me, make sure you can see that I changed the slide. Let me know if you can't. But I thought this quote was fitting. I saw it the other day. It said, "Old ways won't open new doors." And don't look into this too much. This is certainly not to say, hey, we don't have a good process and that we haven't done some neat things and that technologies we've been working on aren't good. I recommend a lot of them all the time. This was more to get us thinking, hey, do we get caught in old ways of thinking? Or if we go to these same conferences or the sessions on some of the same technologies and topics for the past years, do we get caught thinking inside the box sometimes with like management in particular? So again, this is not to pick on any process or method or product. It's just to beg the question, hey, is there something different we can do, something better out there to open our eyes to new ways of doing things? And in particular, we're going to talk about nutrient binding today and phosphorus mitigation. So on this line of thinking, is there new ways to mitigate phosphorus in aquatic systems? What I wanted to show you right up front is a quick Google search I did. These are just some Google Scholar papers. I mean, literally minutes that I spent looking online to find some of these. You see literally hundreds of things out there that combine phosphorus. These are just a few of them that I snipped out that you can find that are publicly available. There's a lot I can't talk about, but things like zirconium, phosphorus adsorption, onto different nanomaterials, different, this one's fun, upper right, nanobimetal ferrites. There's a lot of different modified biochars. In the bottom right corner, sheep manure. That's fun. Oyster shells. So you can find all manner of different things that can bind phosphorus in the literature. This one in the middle is actually pretty cool. These, iron oxide, zinc oxide, enhanced by magnetic field somehow, used in the sewage industry, can have a huge binding capacity for phosphorus. Some of the highest reported phosphorus binding that I've ever seen, and they can actually work really well. So again, literally just with a quick search, a quick look in the scientific literature, you can find hundreds of different materials that have huge binding capacities and specificity for phosphorus in particular in this case, and certainly things for other industries and constituents of concern. Now down here, coal fly ash, that should raise some red flags. Bottom ash, I wasn't quite sure what to think when I read that. There's probably a joke in there somewhere, but we'll keep it clean today. But again, many different things out there, new things being developed, being published on and researched that combine phosphorus. And that sort of begs the question, is there something better out there? Now, many of us, if we were asked, hey, what talks were at NALMS this year, or sessions, or what things bind phosphorus, we jump to, aluminum-based compounds, maybe alum, polyaluminum chloride, and those are great. I recommend them all the time. Recommended some yesterday. This is not a negative on those. We spend a lot of effort and research into those, and in particular, Dr. Wegner has some great things. So this is not to say that what we have is not good. It's to say, is there something different or better out there in some way? Now, better is a vague term, understandably. Is there something better on an ecotext side, a specificity, a degree of binding, a cost or operational side of things, a capacity for phosphorus binding? So again, this is a vague term, and really the science and years worth of science needs to go into understanding these before they should be applied widely in aquatic systems. But that also begs the question: who's doing this? Who's developing new things? Who's looking at these technologies? Who's speaking at NALMS on some of these things to lake managers? Because I would say pretty confidently that, yeah, of those hundreds of compounds published on that bind phosphorus, there might be something better. There might be something better in many of these different categories. So again, that was more of a quick opener. I'm going to shift gears a little bit and talk about some of the things we're working on and developing. And again, there'll be multiple new things that we're trying to develop and launch for use in water resources and lake management. But again, just trying to open our minds here and let you know there's more things out there than you've probably heard about, and some of them have merit, a lot of them don't. A lot of them couldn't check some of these boxes, a lot of them could, and there's still yet a lot of testing that needs to be done. All right, so switching gears to some of the research we've done, looking at some of these products and technologies and trying to develop something for you. And sorry, the slide keeps going, but we really see this this watershed, this inflow, as a key area to intercept nutrients. We think this can complement watershed practices very well. So very, very important to have those stormwater control measures and BMPs and things in place in the watershed, but those can take time and cost to implement, and sometimes they just miss some. Some of them have built-in bypass devices where innately you miss something coming in, and there's often still a lot of nutrients in these types of inflows coming into a lake system. And they can also complement those in the water resource itself practices. So I'll give you an example. We did a Phoslock application. It seemed to work really well. Then we had this big flush event, big gully washer, if you will, 5 inches of rain, and it just brought in a lot of nutrients on top of that Phoslock layer. So really to complement the effectiveness and ability of those in situ control measures to work better is where we saw a critical need here we focused on for some intercepting nutrient research. Now this, there's many concepts here, and we'll talk about some of the existing ones, but one of the key ways we found that could work to be efficient to deploy these is a mesh bag that encompasses and holds in the filter media. And there's, I think, some neat benefits to that it maintains in that mesh filter, and as the water passes through and connects with this material, that it's able to bind that phosphorus very specifically out of that inflow water. And just sort of back up, and these are not specifically ones I put on that first slide there, but we tested a lot of different products, a lot of different things out there claim to be able to bind phosphorus. Just go look in the literature, go look in the aquarium industry, if you will. There's many things out there that say they can bind phosphorus. Some don't. We saw a couple spikes in some of them. They released phosphorus. Some work, but we were able to, put some testing in place to look at a lot of different materials and combinations thereof to see what may work in terms of binding phosphorus in a very short contact time scenario or flow through scenario. So that's just what some of these data represent is, hey, we just poured some phosphorus media through these materials and measured what it did in terms of removing phosphorus from the water column itself. Now, there are some existing things out there. You're saying, hey, there's some neat alum inject systems being widely used and effectively used, and that's absolutely right. There's been some polymer blocks widely used, and that can take out phosphorus. That's often designed for turbidity as well. Biochar, activated carbon, certainly can have some impact and remove a lot of different things. So there are some, I'll say, existing, more known things you guys may be thinking on, hey, what can we do with these inflows? But we really saw a neat opportunity for, sort of advancing this. Can we get higher capacity? Can we get more specificity? Can we be more efficient at binding, phosphorus in particular is what we focused on so far, from these inflow waters. All right, so key features, again, you can see these sort of mesh, they're black mesh here, permeable filter bags, if you will, that house the product itself, sort of inert granule mineral inside these mesh bags, and they can be placed in the stream system. So again, the goal is to promote that water contact and penetration through the bag, through the material, and once it gets that contact, it can grab the phosphorus pretty rapidly on those available binding sites. So we did find a very high specificity and capacity with these mesh filters with the technology that we were able to find and put in there. It didn't change the pH of the water that passed through. A very inert sort of mineral proprietary blend we found. And one of the neat things is not much entered that dissolved state or the water resource itself. So one of the biggest concerns, if you will, with a lot of the algicides we work with, or herbicides, or even water quality or nutrient mitigation products that you put in receiving waters is they're out there. They stay in the system itself. And that begs the question, hey, what's the fate? What's the ecotox? How long does it last? A lot of those things. How does it behave under different environments? Does it re-release it? But the neat thing about these is they're designed to be put in and taken back out. So they can specifically bind the phosphorus in that mesh on that mineral, and then you can specifically remove it from the system. And there may be a couple fines that come out of here. I'm not going to say nothing comes out, but the vast majority of the material itself, again, stays in there and doesn't end up in the water resource itself. So it's very inert as it is. I'm not worried about the ecotox, very positive ecotox profile. So if it happened to spill out and go out there, it's not a big problem. But again, it's designed not to leave any residual trace of anything or very minimal in the receiving water itself. All right, so what can this version do? And we're continually making improvements. But what we see here is one filter. The black mesh sock, if you will, or filter is 25 pounds currently, and can remove over 0.25 pounds of elemental phosphorus. Now, more specific to the phosphates, polyphosphates, I think more of that free reactive phosphorus it likes to bind up preferentially, which we see a lot in those inflow waters. Not, some turbidity will get hung up on it, but it's not like a polymer block designed to coagulate and drop out, sediments, if you will. But we see over a 1% phosphorus removal capacity by weight, and I'll show you some of the data we use to calculate that here shortly, or around 10 milligrams phosphorus bound per gram of Utrisorb. So again, that means right around 100 pounds of this product binds 1 pound of elemental phosphorus. And that, there's different, ways here, but in general, if you look at the phosphorus content of algae, and they can shift it, and there's a range, but it can support, around 500 pounds of algal growth you see, just based on its sort of phosphorus content in the biomass itself. So again, with a few of these filters in this inflow media being able to capture a lot of this phosphorus, you can really offset some of the potential negative impacts of algal growth and eutrophication in the water resource itself. So again, just a different way of looking at it is, hey, can we take out, if we took out 50 part per billion, which is around half pound of phosphorus, or what two of these filters could do, could we shift it back to a more oligotrophic, mesotrophic state in a typical 1 acre pond? So again, we've seen some neat benefits of this, and a neat focus area that I think needed a lot more work in terms of those inflows of nutrients. So I just want to run through some of the preliminary laboratory mesocosm data we did, end up alluding to the field. I'll make sure I'll stay on time here, but this was just some of the initial trials we did where we mixed some of this Utrisorb product up in a beaker with spiked concentration of phosphorus, and then just measured in that that water after a certain period of time. We saw very good removal in that mixed setting. So you may attribute this to, hey, if we can attach this to a fountain and push water through it, it may work too, even in a static water body. This was pretty neat. You may say, hey, there's still, a couple thousand part per billion of phosphorus coming out. We spiked it to over 5,000, but this was a really early study where we basically just poured phosphorus media through a pretty wide clear tube, and we saw very rapid binding. Was the neat thing is, I mean, we're talking seconds of contact or less as this media is passing through, or the aqueous spiked media is passing through the material itself, and saw very good removal and continuous removal. Spent a lot of time just pouring prepared media through, 100 liters plus we were pouring through in this scenario, and it was still removing quite a bit of phosphorus coming out. Now, if we slow down the flow, this is a little different graph, a little different starting here, but if we slow down the flow, so as pushing through a larger diameter of media, there's a lot of factors at play here. You flow, contact time, bag placement, number of filters, if you will. So there's a number of things we have a use guide, but if we were to slow it down, intentionally we were looking for a capacity in this research. So this is much slower flow, so you see much more contact we were getting. And that was able to remove a lot more phosphorus. So it does have the ability, with a longer contact time, saturate those binding sites, get much more removal of phosphorus, even with over 2,000 part per billion phosphatous phosphorus coming in. And we were able to continue that out even to 150 liters. Now you start seeing, hey, as some of the binding sites get saturated, or the more readily available ones, your efficiency goes down a little bit. So, we're going to 99% removal, creep back up to only maybe 60% removal after 150 liters. But this was just 30 grams of the material itself. So still pretty impressive. Again, this could be overcome if you wanted to keep that down by switching out the bags or adding more bags in sequence behind it. So again, we have a use guide. We can help guide you here. Every scenario is a little different, but again, this was driving through the same media, trying to drive it to capacity. And I'll show you some of those calculations here right now. Is if you basically took that that peach area, what was removed, times that volume that poured through it, you could add up all these milligrams. So micrograms here shown, and change those to milligrams of phosphorus, and throw that up here. And this is how we can get a capacity here is, hey, we got this many milligrams per 30 grams of material, or 10 milligrams per gram, or 1% capacity. Now, it would continue to remove phosphorus for quite a while. I wouldn't say we did it until we reached that breakthrough point where it's the same coming out as coming in, because that's a lot of liters. So again, the capacity is, I'd say, greater than 1% has the ability, but again, this is forced contact. It is that media going right over the material itself. So field results, you may or may not achieve that exact removal based on how things are placed out there. So I think placement's very important. All right, let me keep going here. Another beaker study, again, just driving to capacity, where we mixed it up in a static scenario, tested different materials, combinations thereof, but we're able to achieve our 10 milligram per gram, our target capacity for removal there. We've done some things with mesocosm flow throughs, where we basically had well water in this scenario spiked with extra phosphorus, phosphate, and just pouring through these Utrozorbed filters and measuring it coming out as well. So again, very effective even on those larger scales. But again, just promoting that contact and pushing through the material is a key factor of this technology. This was a mixed up reservoir, just 1,000 liter big horse trough, if you will, very high phosphorus starting levels, where it's just sort of mixed up with that Utrozorbed filter, but we were able to achieve that target capacity, is that red line there, and got continuous removal from these static mixed reservoir systems too. So pretty consistent results in terms of, hey, if the water contacts it and has phosphate in it, it binds and it holds it. We didn't see any depuration. I certainly poured some just DI water across that Utrizorb in the tube itself and didn't see the desorption or depuration of the phosphorus. So it seemed to hold it really tightly even after being dried out. And interestingly, I didn't show those data, but after being dried out and pour more phosphorus in it actually got better removal than where it was sort of left off wet, and attribute that just to the water being able to get in those extra crevices after they had dried out. So again, no desorption, maybe even more binding after drying out. So there are a lot of factors here to consider that we're working through. You can see, hey, in the field, in some of these streams and near culverts where we put it in, hey, sometimes it's sitting down in the mud, and sometimes this acts almost like a sand filter and picks up some turbidity and could act as a barrier. So rotating the product, changing how it's positioned in place, multiple filters in a row. So there's a lot of site specific factors that can alter, hey, how well is this going to work? And certainly we can provide guidance on that if needed, but we do think when done appropriately can provide very effective control and really be tailored to a lot of different sites and open some new realms of water resource management in particular. But again, there's a lot of things we're improving and working on. I can't go into too much detail here, just that we do have a provisional patent on some of the things we found to enhance the water flow and contact through there and keep that binding very rapidly, especially under higher flow scenarios. So more to come. So couple quick field examples. I'll wrap it up and open it up to questions here. But this is a small creek system, high phosphorus coming in, causing eutrophication. The receiving water, this is actually out in Colorado. Not our data, but were shared with us some of the initial trials we did. But we're able to put a series of Utrizorb filters down this stream. And here's just some of the data shared. Again, there's going to be some variability, but we did see a decrease in phosphorus. The orange line there is downstream, a downstream sample after the Utrizorb filters versus upstream. And again, it's flashy, as you'd expect, a little tricky to monitor in flowing environments, but we're getting better at it. And we have a couple of those lifetime sensors we're working on developing and deploying as well to get us much more data points to show what it can do. But again, positive to see a difference between downstream and upstream samples there. And if we incorporate the flow volume into that times the concentration, we do see pretty substantial reductions in sort of the phosphorus in terms of a pounds or mass that's coming into that receiving water system. So we do see, again, preliminary data. Still have a lot of field sites we're working on, certainly looking for more if people are interested in doing some work on this. But initial results look real positive. Here's another example into a pond. You see the stream coming into the pond, only about 0.3 CFS. We're working on getting into some larger systems. You can see the mesh filter placement here, trying to promote that contact with the material itself. We did see, again, some variability here, but we did see some differences at multiple time points post-treatment in terms of phosphorus concentration, and that also showed a difference with sort of that mass of phosphorus times that flow and volume coming in at each of those points. So one more example, and this is anecdotal here, although the superintendent seems very happy. This is a golf course actually in the Northeast, and one of the initial users of this technology. Always had issues in his pond, algae issues, but he said the clarity was the best it's been and very minimal algicide needed after placement of Utrizorb. So again, not necessarily hard data, but if you talk to the superintendent, he was pretty thrilled about some of the transition he saw out there. So again, still early, still we're less than a year really getting some field experience with this. Very positive, but things that open up a lot of new realms in the profession. See it able to be placed at many different types of use sites at many different scales, again, to complement those BMPs or stormwater systems, even potential to incorporate this into bioretention cells for example, or SCM. So we do see more and more discharge permit levels on phosphorus from all sorts of systems, from canals to wastewaters, TMDLs. So we think this tool could be, one more in the toolbox to help achieve those management objectives. And we are, working with a number of lake management companies to secure these in a system itself and sort of circulate that water through those to promote contact. So I do think it has a fit in other areas where you can continuously, move that water across the media. So just a couple, snapshots. These are fairly common HOA or stormwater ponds where you have these types of point source inlets, and that can bring a lot of nutrients with it. So to have these placed around here, I think could really help us be more proactive on intercepting those nutrients before they get in the receiving water itself, and complement both the, whatever we do in the lake itself and complement those upstream areas. So we won't get into this too much, but again, I think it can complement and sort of fit in a more holistic nutrient management plan and fit in and complement these other BMPs and SCMs that you may be implementing. So summary here, again, a lot of us, if you look at the program and NALMS and some of these other conferences, hey, we see some common things that bind phosphorus and some common ways of doing things, but we're trying to think outside the box here, trying to develop and investigate some of these new things and mixtures thereof, and try to fit a need, a niche in water resource management. And we do think this technology has a neat fit to help us do that, trying to offset the need for reactive treatments, offset that growth of nuisance and noxious algae in these aquatic systems if we can get and intercept those nutrients. So again, technology very ecologically benign, minimal impact, minimal product, if you will, actually ends up in the receiving water itself. We're able to grab that phosphorus, very specific to phosphorus, and then remove it from these ecosystems, and a potential recovery reuse message as well with the media and the phosphorus itself. So again, see this as a neat new fit, and water resource management opens a lot of realms in terms of areas that can fit in. So with that, I hope you guys can see me okay, and love to answer any questions. I think I have a couple minutes, Heather.
Yeah, thanks so much, Wes. Yes, we do have a couple questions. I've got a couple here that are pretty similar, so we'll start there. Can the bags be reused? The filters or the bags be reused? And how do you dispose of them?
So yeah, those are good questions. So it can be disposed of just in a landfill. That's not ideal, but it can be pulled out and disposed of in a landfill. But it is actually can be used as a beneficial soil amendment. So you can mix it into the soil. It's not going to hurt anything. We're doing some research there and have some use guidance potentially on that. But yeah, the technology itself can be used. I won't say fertilizer, that requires some other check boxes, but yeah, you could just throw it out, but you could also incorporate it as a soil amendment or media. What was the first part of that question? The bags be reused. Oh yeah, so there is a potential on the media itself. So we can add something to it and pull the phosphorus back off of it and sort of recharge and reuse that media. The only problem with that is operationally, you got to either ship it back somewhere or have that process there. It just becomes pretty laborious to do that. And you have to use some chemicals to pull it back off. Then you got to realize what you got to do with those. And right now the cost of phosphorus isn't high enough to really warrant that process, but it is feasible. We could recharge the media, if you will, or pull the phosphorus off, and then that media would still be able to bind more phosphorus. So
Great. And what is the ultimate fate of Utrosorb? Is there a particulate that settles?
So the particulate is that mineral particulate is designed to stay inside that mesh. So we try to create that mesh so all those particulates sort of stay in there, and they have, of course I didn't show a picture, but they're very jagged edge, high surface area, trying to promote that contact. That's where the phosphorus is interacting with. So again, they're designed to stay in that mesh, and the fate of them is in there. It just binds a lot of phosphate to it. So again, the ultimate fate would be, hey, whatever you end up doing with that mesh sac that you pull out would be that mineral with the charged phosphate on there.
Great. And should the use of these be after any soil contact? The photo looks like it will go across more soil. Wouldn't that pick up more phosphorus after going past the media?
Um, yeah, so soil and sediments are tricky. That can have a lot of phosphorus with it. You know, what form is that phosphorus in? Is that going to bind to Eutrizorb? The soil and sediments could almost block it and clog it up too if it gets buried. So there's some pros and cons with the soil and sediment side of things. We'd have to sort of work through and talk through. I'm not sure if I fully answered that question appropriately, but you can certainly reach out to me directly and we can talk through it more.